This is the fifth in a series of discussions on science from the Lyndon LaRouche outlook. This being our fifth class, just to recall briefly where we've come. In the first, we looked at the work of Plato and Nicholas of Cusa to get a sense of the relationship between our senses and knowledge, whether ideas come by making inductions from what we've seen, or if the mind is bringing something of its own to that. We heard from Cusa about how knowledge is always provisional, that however right we may be right now, none of our concepts are exactly right. And we can always be more imperfect. I mean, less imperfect. In the second, well, we can be more imperfect too. That's true. We see that. For the second class, we looked at Kepler and a specific example of applying this method. Kepler said that the purpose of astronomy shouldn't be to just know where in the sky you see a planet. It should be to know why they're moving. This is something Leibniz came to later when he said that if motion is only relative, if you have two objects and they get closer, you could say this one moved, you could say this one moved, but the only way to really answer that would be to say, well, what made the motion occur? That's what makes motion real. In the third class, we saw how Pierre Fermat upgraded the idea of cause that exists in science. And he said that final cause could explain phenomena. In this case, the least time principle of light, which has become the general principle of least action today. And then fourth, Leibniz. Last week, we looked at how Gottfried Leibniz put these ideas together and created a new metaphor, a new language that allowed observations and the causes of those observations to be brought under one common understanding by introducing the differential. So something that you're measuring also has a way that it's changing or a cause of its change. And Leibniz found out how you could bring that in directly and connect the two. So very powerful. Today, what we're going to do is take a look at Lyndon LaRouche's relationship to the discoveries of Carl Gauss and Bernhard Riemann. We're definitely going to be focusing more on Riemann today. I'll give an overview of the importance of Gauss, and we can get more into him on Wednesday. So speaking autobiographically for a minute, when I first got involved with the LaRouche movement around the year 2000, 2001, it was a time when there were many young people becoming involved. We would have events with over 100 people, under 30. And during the Q&A discussions, LaRouche was noticing something about young people at that time, namely that most of us didn't really know much of anything. And he said the antidote for this was to work through Gauss's proof of the fundamental theorem of algebra. And that might sound scary, that name, but we'll get a brief idea of what that means today. Then we're going to take a look at Riemann, who developed a new idea about the shape of space in a way that prefigures Einstein and also Planck, and how that had a bearing on LaRouche's idea of understanding the value or the meaning of scientific and technological breakthroughs. How do those create a new platform of life? So where we're at now is looking at the effect and use of Carl Gauss by Lyndon LaRouche. So Gauss's paper on the fundamental theorem of algebra, we'll get to algebra in a minute. I want to pose some questions about just plain old numbers, about arithmetic. And I will be keeping an eye on the chat, so you can contribute that way, or on, or by raising your hand and so forth. But I want to start by making sure that, see how comfortable we are with the idea of numbers that are prime or not prime. Can anybody say what makes a number prime, what this concept means?
Divided by any number except for itself and one.
Oh, and can you give 3 examples?
17.
Okay.
5.
5, all right.
7.
7, okay. Yes. So prime numbers can't be divided by anything besides themselves and 1. Another way to put it is you can't divide it into a bunch of equal piles, or you can't form a prime number into a rectangle except when one of the sides of the rectangle is 1. So that makes a number prime. So Margaret named a few prime numbers. The last two were 7 and 5, I think. Now, if we multiply those two together, we get 35. Are there 2 other numbers that we could have multiplied to get 35 besides 7 and 5 from Margaret? Is there another way to get that number by multiplying?
Not by whole numbers,
Not yet, not by the whole number.
right?
No, I don't think so.
10.
35.
Say again. Joe, say again.
1 and 35.
Mhm.
Yes, that's true. Is there a way to get 35 by multiplying 2 numbers, not using 1 and 35? Come on, without doing it by doing 5 times 7.
3 and 15.
3 and how much again?
15, I think.
45.
45,
3 and 15.
no, 3.5 I did.
Oh, Kevin wrote -7 times -5. Okay,
Yeah, it's
very
good.
clever.
Yeah.
Okay, so whole positive numbers. Jose says, no, there's no other way to make 35. Okay, now we're gonna do it another way. We're gonna start with a number, and we're gonna see if we can find multiple ways of making it out of primes. So I'm gonna think of a number, and my number is, this is very difficult,
Why are we watching Tom's?
60.
Because he put his
So-
video.
Yeah.
So take how about the number 60? What prime numbers can we multiply together to get 60? And let's see if we can find more than one way of doing it. You can type in the chat, you can unmute, you can speak up in the room. Getting the number 60.
6 and 10.
6 and 10. Okay. So we hear that 60 is made of 6 and 10. Now, how about 6 and 10? Are those prime numbers?
No.
No.
Let's break them up. Well, how do we make 6?
2 and 3.
2 and
2
3.
times
How about
3.
2 and 5.
2 and 5? Now, those are all prime numbers, right? 2, 3, 2, 5. So 20 is 2 times 3 times 2 times 5. Let's check it, right? Jose is pointing out that there are several ways of doing it. You're right, Jose. There are several ways of getting 60 by multiplying numbers. Question is whether when we break it down all the way into getting 60 by multiplying only prime numbers, are there different groups of prime numbers that we could have used? So the one that we just got was 6 times 10. 6 is 2 times 3. And then 10, now we multiply by 2. So where are we at now? 2 times 3 times 2, we're at how much? 12. And then we have that 5. So 12 times 5. Okay. So 2 and 3 and 2 and 5 went into making 60. Is there another way? Can we get a different group of primes? Richard Burden adds that 60 is also -2i times 30i. Okay. Definitely what we're going for here. All right, how about this? Jose points out that 60 is also 15 times 4. Let's break those up. So 15, what's 15 made out of?
3 times,
And then 4 is,
2 times 2.
so you put that together, it's the same group of numbers, isn't it? Just in a different order, right? 2 and a 3 and a 2 and a 5. Well, it just so happens that if you multiply prime numbers together to get a number, there's only one way to take it apart into prime numbers. If you don't worry about what order you multiply them in. That's the fundamental theorem of arithmetic. And Kevin says there's many ways to do it, but they all seem to involve the same primes. Yeah, that's right. 2 times 2 times 3 times 5 2 times 5 times 3 times 2. When you multiply numbers, it doesn't matter what order you do it in. So we're only talking about what are the 4 numbers that we're multiplying and not thinking about the order. So that's the fundamental theorem of arithmetic. Now what I want to do is take a look, and we're going to be using the board for this, at the fundamental theorem of algebra. First, are there any questions about this concept, that there's one unique way of factoring a number into its primes? Okay. All right, so let's take a look at some algebra now. Okay, we'll zoom in, don't worry, it'll come in. Let's say we have this equation. X minus 2 equals 0. So what is X? It's the number that makes this a true statement instead of a lie. So if X were 4, would this be a true statement? No, it's a lie. So what is the value of X where X minus 2 does equal 0? Okay. Right. And how about this one? X minus 3 equals 0.
It's not
X.
zooming in, Jason.
We'll get there. We'll get there.
Okay.
Ta-da. And then we'll even get it. Perfect. Good. Okay, so here's our two equations. What I want to do is combine these 2 equations, and kind of like multiplying 2 and 3 together to get 6, we're going to multiply these equations together and see what we get. So if we multiply the first one by the second one, we have x minus 2, and we're going to do this geometrically. X minus 2 times x minus 3. And on the right-hand side, we have 0 times 0. A pair of glasses. How are we going to multiply x minus 2 times x minus 3? You've maybe learned foiling and maybe forgotten it too. But what we're going to do is look at this in a geometric way, the way Al-Khwarizmi did. So first off, he says, okay, let's take a line, and let's say it has a length of x. And let's take away 2 from it. So we go back 2. So here's 2. And maybe I should. So x is the full length. And then this partial length is x minus 2. Okay. Now let's take this side of our square. So its full length is x. This time we're going to take away 3. And we will have this length, x minus 3. So what we want to know is what is the area of this rectangle. And I hope everybody can, you could zoom in a little more. It would be okay, I think. I think it's got a lot smaller than when I started. So how do we figure out how big this rectangle is? Let's start with the full square. What's the area of this whole square? It's x on this side and x on this side. X squared. Okay, so we've got x squared, that's our red square. Now what do we have to remove this L-shaped thing to get what we want, right? How big is the whole L-shaped thing? Kind of an awkward shape. What? Let's break this into 2 pieces. Let's first take this whole rectangle and subtract it. Yeah, this rectangle is 2 by x. So its area is 2 by x. We write it like this, 2x. So we had the red square. We took out 2x. So let me erase that. Let's take it away. Great. And if we could just get rid of this part, then we would have the green rectangle we're looking for. What's the dimensions of this rectangle? 3 times x minus 2. Yeah. You know, just to keep everything as simple as possible, I'm going to re-add this little rectangle. How big is this rectangle down here? What are its dimensions? 2 by 3, not to scale. Okay, so its area is 6. So we added 6. And now we have this whole rectangle. What's the area of this whole rectangle? What are its dimensions? Yep, x by 3. I should drown this outside.
3x, 3 fois x.
So we remove 3x. And now we have just what we wanted, x minus 2 times x minus 3. Geometrically, you know, areas are made by multiplying the sides.
Why would you add this?
Because like that, it is more simple to set 3 times x minus 3.5 x minus 3x minus.
The reason was that I wanted to avoid doing this. We could say that this is 3 times x minus 2. And I didn't want to deal with that. I wanted to just make everything as completely simple as possible. So instead of removing this, so we started by removing this rectangle on the right, 2x. I just don't want to, I don't want to do this. I don't want to remove something that's got this complicated side. So if I add the 6 back here, now I have a rectangle that's just 3 by x. Well, because the 6 is already gone. So here, let me do it again by shading in this time. So we have our whole square. Okay, that's x squared. And then on this side, we went back by 2. On this side, we went back by 3. And our goal was to get this green square, x minus 2 by x minus 3. Reminder, don't erase with your finger. Then when you write, it doesn't work. Okay. Okay, so we want this green square. So my idea was first to remove this whole rectangle on the right. How big is this rectangle on the right? 2 by x. Okay, now I'm gonna use some spray this time and remove it. Okay, so it is gone. So we've got, so far we have x squared minus 2x. Is that fair that this is x squared minus 2x? So now the question is, why on earth did I add this 6 back in here? Let me pose it a different question, pose thinking about this a different way. I'm going to add the 6 back and see if you agree with what happens. Sometimes the y comes after, you know, what's going on. So just bear with me here. If I wanted to add this rectangle back,
This rectangle belong to
yeah, this little rectangle is 2 on one side, 3 on the other. How much is its area? Okay. So I just keeping track of what I'm doing. I added 6. I added it to the drawing. And now, what is the area of this long horizontal rectangle? 3 on this side, x on the other. So if I take away 3x, I've got what I wanted, x minus 2 by x minus 3. So I'm gonna pose a different question. Maybe why I did each of those steps, maybe that's not clear, but do you agree with the conclusion? Sometimes you just have to go with things this way. So let's pull this together. And then are there any? Okay, if there's any questions, raise your hand or type in the chat or unmute and yell them out. So x squared minus 2x minus 3x. So if we're taking away 2x and then taking away 3 more x, what are we doing altogether? We're taking away 5x. We took away 2, we took away 3 more. 1, 2, 3, 4, 5, plus 6. Okay. So what we did is we combined this first equation here with the second one, and we got this one. This is like we multiplied 2 by 3 and we got 6. Can we take it apart and get back to the same primes? And put it another way is to say, well, let's make sure that 2 and 3, which worked here, let's see if they're valid down here. Let's say x is 2. Is this, let's work out whether this is a true statement. So if x is 2, what do we have? 2 squared minus 5x plus 6. 2 by 2, that's 4, minus 5 by 2 is 10 plus 6. And let's say x is 2. Okay, so it's still, so x minus 2 equals 0 is still living within this. And let's try x is 3. So if x is 3, what do we have? We have 3 squared minus 5 times 3 plus 6, which is how much? Help me out here. 3 squared is minus 5 times 3, that's, and then add 6 at the end. If you don't like negative numbers, add up the positive ones first and then do your subtracting. So 9 and 6 makes 15, and then take away 15. A little easier. Okay. Richard Burden says that if x is 2 or x equals 3, there would be no rectangle at all. That's exactly true. This area would have been nothing. If x was 2 and we took away 2, there'd be nothing left. In other words, x squared minus 5x plus 6 would be 0. And if we made x 3 and then we subtract 3, again, we'll have no area left. So the fundamental theorem of algebra says that any equation that's x squared has 2 factors, only 2. It's only one way to break it. X, in this case, x minus 2 and x is 2 and x is 3. And there's no other 2 values of x. The fundamental theorem of algebra says that if, for example, you had an x to the 5th equation, something like this, there's supposed to be 5 answers. Because you had 5 cases of x minus this, x plus that, x minus this equals 0. When you multiply them all together, you get this non-prime number. And can we factor it out into primes in only one way? Now, we are not going to solve this today. We can look at it more on Wednesday, but I want to show you, I want us to look together at how Gauss describes the way that he did solve it. So yeah, now for x squared equations, let's say we have x squared plus bx plus c. Does anyone remember a formula from school that always solves this one? Oh, I can put the a up front. negative b plus or minus the square root of b squared minus 4ac all over 2a. It's 2a. Yep. So definitely not going through this either, but it was certain that if it was x squared, we can always get the two answers. Plug the things in here, you get the answers. Because sometimes if you just look at it, like 5 and 6, neither of these is 2 and 3, but they're related to 2 and 3, aren't they? So x squared, solved. X cubed, more complex, but people could always solve them. X to the 4th, you could always find the 4 things it was broken into. X to the 5th, no one had found one yet. So now enter Carl Gauss. He, at this point in our story, is a he's a 22-year-old. He's finishing up college. He's about to get his PhD. And he, oh, wow. I forgot to mention one extremely important thing. Sorry, Mike. What if I write this equation? X squared plus 1 equals 0. Can we represent that as a rectangle like we did before? How does this work? Is there a value of a number for x? And if we do this, it'll work out. So I heard 1, I heard -1, and I heard x squared equals -1. Let's try -1 first. Let's just see if it works. That was proposed. Maybe that's an answer. So -1 times -1 plus 1. All right, now we have to say how much -1 times -1 is. Yeah. What's the opposite of the opposite? It's the initial thing. So negative just means go the other direction. So if you make 2 U-turns, you're pointing straight again. 1 plus 1. That does not equal 0. So -1 out. Diane suggested if we take this equation and we remove 1 from both sides. This is the last algebra we're doing today. We get x squared minus. This is why it's the last one. This is too much. We have x squared equals -1. Now, because it so often comes up that we want to know the side of a square. In other words, let's say we had a square of 3, and we wanted to say what times itself is 3. There's no answer. So mathematicians invented a symbol that means I give up, I don't know. This is an unsolvable problem. X is, well, the side of a square of 3. This is just saying the exact same thing as this drawing. So here, say, okay, we've got a square that's -1, whatever that means, and we want to know what are its sides. There's no answer to this, no real answer. There's no geometrical answer in the way that we had been looking at numbers. But, yeah, right, an inverse square. So mathematicians said, well, that's fine, square root of -1. I mean, we say square root of 3, so how about this? And it was sort of accepted, it sort of wasn't, because it helped people solve problems. It sort of got some credibility, but the nature of this thing is it was totally unresolved. It was treated basically as a symbol. So now enter Gauss and pull out your reading. We're going to take a look at, let's see here. We're going to look at section 9 in Gauss's proof. This is on page 4 of the handout. I'll put that on the screen. And we're only going to read a portion of this. All right. So who would like to read part 9? We're going to read just up to the bold. Go for it.
Against this reasoning, one can object that after so much labor of such great mathematicians, there is very little hope left ever to arrive at a general solution of algebraic equations. It seems more and more probable that such a solution is entirely impossible and contradictory.
Okay, so I said before, people had solved x squared, x cubed, x to the fourth, but nothing beyond it. Here's Gauss saying maybe it's not possible. And then about the last full part of that. But please continue reading.
Oh, this must not at all be considered.
The part in bold at the bottom.
Oh, okay. It is perhaps not so difficult to demonstrate quite rigorously the impossibility already for the 5th degree. I shall report my investigations of this matter more fully in another place.
Okay. So here's Gauss getting his PhD. He's proving that you can always solve these things. If it's x to the 5th, there are 5 solutions. But here he's just saying maybe there's no way to find what the solutions are. So how on earth is he going to write a paper saying that they have to exist if he can't say what they are? Can you know something exists without saying what it is exactly? Now, one thing about the square root of -1, take a look at section 15 on the next page. And if anyone here or on Zoom, feel free to just unmute and read it. It's pretty short.
Read it. The outstanding theorem is frequently proved with the help of imaginary numbers, CF Euler. I consider it worth the trouble to show how it can easily be elicited without their help.
And indeed, in Gauss's whole paper, his proof, he never writes the square root of -1. Instead, he writes, take a look at what we've got here on the left. We're not going to read this out loud, but
Oh my God.
cosines, sines, what is going on here? Let me just show a picture of this. And this will be the 2-minute version. Not all make total sense, but the gist is what's important here. Gauss ends up looking at the problem geometrically. He creates 3-dimensional drawing. He has one surface, he has another surface, and he shows why the surfaces, there must be spots like this one, where the red surface hits the blue plane, the green surface hits the blue plane, and they touch each other. The axis is very faint, but can you see how where this point is labeled? Where they come together right here?
Yeah.
Yeah.
What is it? Two.
Two.
Hard to see. And then here's the other
If
spot.
you're looking at these lines,
Yeah,
if you imagine the
1,
lines on the
2,
plane.
3, 4, 5.
Yeah.
They're faint. They're faint. Here's the other spot where the red and the green and the blue come together, and it's at 3.
Here, it's not quite on.
Wow.
There's
It's
Oh, yeah,
probably
there it is.
right at 3.
3 what?
Yeah, I don't understand what you're saying. What?
it's three.
I don't see these numbers.
Well, this is the
Three-dimension.
shape of the equation that we were looking up. I forgot to say that. This is x squared minus 5x plus 6. The rectangle that we made. It had solutions at 2 and 3. Just showing geometrically that they're there. Now, just to put up one more picture, this is the one that Gauss has in his paper. It's more complex. And
Wow.
the way Gauss shows that these surfaces have to intersect each other in the plane, it's geometrical. It's really not based on finding out exactly where, but instead it's based on being able to show that their non-intersection is impossible. They have to be able to touch each other. So more on that on Wednesday if people want. what I want to do with that is just see what LaRouche had to say about the importance of this paper. Why was this paper so important to him? So we'll take a look at the first page on the reading. And this is from a paper LaRouche wrote in 2003 when this was all the rage. Mary Jane says, doesn't that say something about the nature of space? Complex space, it does. But we'll say more about that on Wednesday. Okay, Denise, you raised your hand. Would you like to read? Denise, did you mean to raise your hand? Okay. Well, I'd like to get a reader, and I'd like to get an online reader for this one. And especially if it's someone who hasn't read today, yesterday, or last week. Any volunteers?
Can you hear me?
Sure can.
Okay. I shall show here that the unstated but implied aspect of the charge which Carl Gauss delivered in 1799 against D'Alembert, Euler, and Lagrange lies in the implication that the latter were virtually Satanists, that in the sense of the philosophical tradition of both the medieval William of Ockham and those founders of modern empiricism, Venice's Paolo Sarpi and his personal lackey, Thomas Hobbes' teacher, Galileo Galilei, I shall show here without exaggeration of any kind that that charge of Satanism is not merely relevant, but must be emphasized to bring into focus the implicit, most essential features and political importance of Gauss's argument respecting mathematics itself. I shall also focus some exemplary attention on the leading role of empiricism in producing those widely accepted and competent doctrines of economy, such as contemporary monetarism, which have played a leading role in bringing about the 71 to 03 collapse of the economies of Americas, Europe, and Japan, and elsewhere. As I have
That ends at 2003 because that's when he wrote the paper. That's when the economy turned around. The names that Lynn mentioned at the top, D'Alembert, Euler, and Lagrange, in Gauss's proof, he's 22, right? He's getting his PhD. He's like a kid, basically. He goes through and shows why these guys' proofs didn't work, why they were wrong. And so half of the paper is a polemic about what's wrong with the way people are trying to solve these problems. Then he gets to offering his own idea. Okay, go ahead and continue, Denise.
As I have shown in locations published earlier, the crucial quality of functional significance of philosophical reductionism, such as empiricism, for physical science is that it attempts to uproot the knowledge of the existence of what the celebrated geobiochemist V.I. Vernadsky identified as those noetic powers of the human mind which distinguish human beings from beasts. Within the realm of political science and law, that denial of the distinction between man and beast is the philosophical basis for Satanism. Typical are the synarchists and kindred followers of G.W.F. Hegel and Friedrich Nietzsche. In a narrower aspect of that specific issue, as implied by Gauss's devastating exposure of a fraud in the work of Euler and Lagrange, the specific philosophical expression of Satanism, called empiricism, is the axiomatic basis for not only that radical positive's aberration, which is known as the so-called new math, but what has been usually recognized even earlier as today's generally accepted classroom mathematics, and the economic fads of the positivists.
Okay, much as I hate to do this, I'd like to jump a few paragraphs. Please read this on your own, it's wonderful. And yeah, Rick.
What's the difference between mistake and fraud? Do you think it was a mistake or a fraud? Fraud is a willing mistake, is it not? A willing, lie or misrepresentation.
Or yeah, like you
these
should have
guys-
known better or could have, you had available to you the ability to know that it was, or like you could have, you had enough to be able to figure out that it was wrong and you chose not to. So sometimes just like refusing to pursue something you don't want to challenge your belief and you stick with it, that might also be a kind of, I think you can be fraudulent without lying if you're willfully indifferent.
Do you think these guys were?
I don't know them well enough to say. I know what Lynn is saying here. I try not to say things that yeah. I mean, one
Were
of
they alive at this time?
I think Euler was dead. Lagrange was still alive. Lagrange was Napoleon's favorite mathematician, and France was about to take over the part of Germany Gauss lived in. So he's really taking a risk, insulting him this way. But when you see what the central part is of his objections against these guys, it's almost so basic that you have to wonder how could they all have. He says that the negative sum of all the roots would be the first coefficient after the main term. And they say, oh, great, so we'll assume that the sum of the roots is this number. And Gauss says, but you don't know there are any roots. How can you assume that? So it's like right out of the gate, like they all start from that. So in other words, they were trying to do something different. They didn't doubt that there were answers. They focused on how do we find what it is. Gauss had a totally different approach of saying, you can't find out exactly what it is, but I can still show based on the space that this thing is happening in, why they must exist. I know that doesn't answer your question about whether they were frauds, but it was a pretty big mistake they were making, I'd say.
I don't think that is a mistake, I have to say, because if you're that advanced in mathematics, then, and you choose to ignore that you're just leaping to an assumption that everyone has to accept, then you know that that's a lie. Right? If you don't feel obligated to say, why must it be this way? Can I show that it must be this way? No scientist that's fair would let themselves get away with that.
Are you getting, does Gauss talk about this in disquisitions?
This is the most personal that Gauss gets. Gauss is very reserved. So the disquisitions, he talks about math. He doesn't talk about people very much. So this paper of his when he was young and, anyway, different.
Not prudent.
When he was before he was living under a police state, is like as polemical as the guy gets. So if Gauss is an incredible, amazing thinker, this paper is fantastic because you get to see him fighting with people. So I think that's why. Yes, Richard.
One quick thing. When we read this paper with you and Adrian and so forth, the thing that you pointed out, which is really, I think, critical here, is these guys would say, okay, we're going to call the square root of -1 I. And if you have I times I, that's I squared, that's equal to -1. And they use these things, but they didn't ever prove that I is real. And Gauss does, geometrically. He says, you can use symbolism and keep doing all sorts of these rules if you want to multiply a number that's partly real and partly imaginary by another one. That doesn't prove anything. So I'm going to show you geometrically they exist, and no one had done that up to the point of Gauss and didn't even think it was necessary.
Yeah, thank you. That's the central part of what Gauss does is by making the square root of -1 not real not imaginary. He says, don't call it I or imaginary number. That's insulting. It's not imaginary. It's just complex. All numbers are complex. So square root of -1 is what Gauss writes. More on that on Wednesday. Okay, Margaret, briefly, and then we got to move on to Riemann.
No, the idea of simply saying, well, we just won't go there, and we'll punish anybody who does dare to go there, is like the ban on the diminished fifth, the tritone. It was called the devil's interval, and people could get severely punished for using it in music. When it turns out, as we know from the more modern period, that interval is one of the key stepping stones to being able to utilize the entire musical universe.
Another example, good. Okay, let's continue on the bottom left of page 2. We'll finish up this quote from Lynn, and then we'll get into Riemann. So we need someone in the room. Yeah, Mike, go ahead. As I shall show here, in the bottom left on page 2.
As I shall show here, the influence of such reductionist currents of popular opinion is such that the attempt to teach Carl Gauss's 1799 treatment of the fundamental principle of algebra would often fail, simply because the teacher were lured into attempting to prove the existence of the ontologically complex domain within the bounds of the presumptions which bow to the currently most widespread classroom and related opinion. Classroom opinion on many topics is widely polluted, still today, by the prejudice that all must be proven according to the popular presumption that truth lies ultimately, axiomatically, in the domain of the so-called real counting numbers of simple sense perception, as distinct from the higher standpoint which Euler and Lagrange maliciously libeled as the domain of imaginary numbers. The point emphasized here is that it would be an intellectually fatal tactical mistake to attempt to show a devout reductionist an argument for the Gaussian complex domain in terms he is willing to accept, terms which are bounded by the essentially linear axiomatic assumptions of arithmetic reductionists such as Euler and Lagrange. Therefore, for such an errant discussion partner as one of the latter ideologues, only that kind of classically Socratic argument for the relevant hypothesis, which would blow his beliefs apart emotionally, could actually show him the incurable folly of Euler's and his own argument, as I do in this report. The use of this method of hypothesis means attacking the falseness of the reductionist's fixed ontological assumptions, not in his choice of method, deductively, but epistemologically, emotionally, rather than merely deductively. On this account, epistemology, it was the relevant specific virtue of that 1799 Gauss piece, which had prompted me to situate it as the cornerstone of the initial educational program of the youth movement. The immediate issue of the dispute over that piece, from the close of the 18th century to the present day, has been, as Gauss's enemies themselves emphasized at that time, Gauss's insistence on viewing problems of modern mathematical physics from the standpoint of a classical pre-Euclidean geometric treatment of those same errors, which Gauss exposed as the products of the ivory tower mysticism of Euler and Lagrange.
So Lynn was calling empiricism Satanism here, right? This opened up, this is the beginning of this paper. It's actualizing the complex domain, which is what Gauss did geometrically. If real numbers, essentially the dispute here about real numbers and imaginary complex is like the shadows versus what is causing them. You have a real domain of observations, but there's a complex domain of causes. This isn't as direct a parallel as Leibniz's infinitesimal, but it's a similar issue here. Okay, so if you want more on this, and I hope you do, Wednesday night. I just planned too much for this class series, so we're going a little fast. I mean, each of these things could be 5 weeks. What I want to do now is jump ahead to Bernhard Riemann. Now, Riemann, who lived from 1826 to 1866, he was one of the core inspirations for Lyndon LaRouche in his own economic insights. So LaRouche writes that he had a concept of the relationship between scientific progress, technological advance, and then the economy that could be supported based on that. But what's the groundwork for, how do you put that into practice as an economist? And he said that Riemann really helped give a way of doing this. So I've got a few short quotes from LaRouche. This time we'll start with LaRouche and then go to Riemann. Let's read the first one of these LaRouche quotes. It's on page 8, and it is time for a reader from online. Please raise your hand. And it's open. Anybody online?
I'll do it, as I haven't gotten there yet.
Okay, this is a 2001 paper.
The universe is multiply connected in the Riemannian sense. This has the essential implication that the addition of a new principle to the manifold results in a change in the characteristic curvature of the manifold as a whole. This means that the value, the impact of each such discovery, changes the value of each previously established type of action within the thus unfolding manifold. So, for example, a successful such change within the technology of a society will tend to increase the effective productivity of even those forms of action which are themselves changed otherwise. So,
excuse me, which are not themselves changed otherwise.
I'm sorry, yes, forms of action which are not themselves changed otherwise. You know, these old guys, they play tricks on you. So, a genuine improvement in the basic economic infrastructure of a society increases the productivity of otherwise unaltered modes of productive action within the society as a whole. By definition, no mathematical model of the Descartes-Newton type could represent such connections and effects.
Would anyone like to, so what's he saying here? Would anyone try to put this in their own terms, or what's LaRouche getting at in this?
I know that he made it of the application of electricity to machine tools. They used to use a single belt controlling all the machines in the factory, run by some steam engine somewhere. And then when they applied the electric motor to each individual machine, the productivity increased dramatically, even though the machines were doing the same thing.
Perfect example. You change the space in which economic activity is occurring, and even the parts that aren't locally changed still differ in their effects.
Well, they suddenly also, it would mean the machines are all independent, which was a completely different character than what you had before.
Then it opened up new ways to actually change the machines themselves too.
Right.
Now you could use electric motors to do controlling and not just providing the power. So yes, good. Okay, let's go with the next reading from 1996. I think that we had just had a online, so it's time for someone in person. You'd be so kind. Go ahead.
If I am conscious of the content of my own knowledge and practice in the manner underlying a classical humanist form of education, then I know that most of what I know represents valid discoveries of principle effected by individual original discoverers, some known by name, more unknown, most located deep in the lost pages of prehistory. In reenacting their discoveries of principle, I have relived in my mind moments from the interior of their own. I am closer to those long deceased persons than to most of the daily associates of my childhood, youth, and adult life. If I aid in transmitting those precious gifts from the past into the countless generations of the future, and perhaps add one or two such gifts of my own, I am certain that my own life will have been a necessary one, both a fulfillment of the past and a gift to the future. I have thus met the test of death. Everything we have said here on this matter to the present moment of writing is premised upon and delimited to statements respecting the set of relations defined by the general principle of hypothesis, even as Riemann's 1854 habilitation dissertation expresses that Platonic principle as its pivotal foundation. The general set of relations defined by the principle of hypothesis are otherwise describable as relations within a hierarchy of available pathways of change. The ordering principle underlying this hierarchy is cardinality, as we have indicated, that principle of ordering of Riemannian physical space-time manifolds here.
Just want to stress this one part of the sentence. Lynn said that Riemann's 1854 habilitation dissertation expresses that Platonic principle as its pivotal foundation. The Platonic principle, I mean, this is just an excerpt, but we discovered some of what that was in the first class. You know something if you discover it. Okay. I would like to do this one.
Jason, before you move on.
Yes, ma'am.
Cardinality in Lynn's last sentence there and its relationship to the Riemannian physical space-time. Can you just say a little bit about that? I don't really understand what it is.
So the cardinality is a reference to contour. LaRouche, in his 1993 paper we're about to read an excerpt from called On LaRouche's Discovery, he credits two people with really helping him put into practice his concept, Georg Cantor and Bernhard Riemann. Cantor figured out, and it's somewhat similar to the way Leibniz created infinitely small things. Cantor looked at understanding infinitely large things. There's more than one idea, there's more than one infinite. And so it's related. Let me just give one example, and then we'll have to have a Cantor presentation sometime, but it's not part of this class series. But just to say one thing about it, how many fractions are there between 1 and 2? Infinite. We can count them up. We can't. If we were counting them up, we'd never finish, right? Between any two fractions, there's always one right in between. You could keep dividing more and more and more. You'd never be done. There is an infinite number of those fractions. Now, what if instead of just fractions, we said how many lengths are there between 1 and 2? How many numbers are there between 1 and 2? For example, we saw on the board earlier the square root of 3. What's the side of a square of 3? That's a number that's in between 1 and 2, but it's not a fraction. There would be an infinite number of those also. Same infinite as the number of fractions, or a bigger infinite? Okay, now the number of fractions, because fractions have numerators and denominators. Are the number of fractions, well, how about this? How about just the number of,
Yeah, how you can be, if it's infinite, it's not. No,
okay, well, let's try that out. Let's try that out. Look, so Margaret points out it's got more stuff in it. So how do we know it's got more stuff in it? Did we count them all up in the fractions, and we counted up all of the other numbers, and then, because we never finished counting them, how do we say one's bigger? Here's another one that might be seem unexpected. How many numbers are there? Whole numbers, whole positive numbers. 1, 2, 3, 4. How many of those? And then how many fractions are there? Which one's got more stuff? Right, Cantor said, but it's the same infinite. There are the same number of fractions as there are whole numbers. There's a way of basically assigning a whole number to each fraction so that you could make a book. It would be infinitely long, but on every page, there'd be a page number and there'd be one fraction written on it, and then a page number and the fraction written on it. And this infinite book would have all the fractions, and it would have an infinite number of pages, meaning the whole numbers for the page numbers.
So doesn't sound like you can finish.
You couldn't finish the book, but if you let yourself go to the infinite, it's the same size book. The number of pages for each fraction and the number of pages for all the whole numbers is the same. But when you allow all numbers in, now square root of 3, e, pi, golden ratio, just anything, real numbers, then even an infinite number of pages wouldn't be enough to list all of those numbers. Okay, I know I didn't justify that for why that's true now, and I'm not, but I'll just leave that as another one. Come back for more of these things, because we can get into that. It's related to that. It's related to that. And so LaRouche took that in economics, that there's a certain, how many things can you do with steam? Let's say we got a steam engine driving a belt, running these, running all these machines in a factory. Are there only a finite number of things you could do with these machines, or are there an infinite number of potential things you could do?
Can't fly an airplane.
Okay, but that's a different question. Could you count up every possible thing you could do with these machines, or is it always possible there could have been something else? Is it infinite? Like, let's say you even have a rock, right? Or like a chisel, you can make a sculpture. There's an infinite number of sculptures you could make out of a rock, right? There's an infinite number of things that those machines could do driven by steam belt. But like Art's saying, you couldn't make an airplane out of it. So there's still an infinite number of things you can do with electric motors, but it's a bigger infinite.
Well, I'm thinking of these peculiar numbers that you were talking about, like the square root of 3. There's a different way that they are generated.
Yeah.
Can you repeat it? Because we're not hearing the room.
Cardinality, or is that?
Diane was saying that with some of these numbers, like the square root of 3, there's a different way of generating them. Yeah. So that's another way of looking at it. If you look at the products of a machine, something made by an electric motor versus the belts and so forth, it might not be obvious in just the thing, but when you think about what made it, what level of technology was required to create this thing. So that's
So it's just sort of ordering of different types of infinity, a principle of.
Let's go with that for now. Yeah, that you fundamentally changed what possibility means. Infinite possibilities, okay, but you could still have more if you change your idea of what infinite possibility is by adding something that generates a new thing that generates. So that's the metaphor there. Let me respond to a few things in the chat. And we'll read this last quote from Lynn, and then we will get to Bernhard Riemann, who, if this is possible, was even more amazing than Carl Gauss. Julian says, to finish the question, is the complex domain actually a physical thing, or does it just have physical effects? Well, that's right on. So the question of whether change is something that's real, this is a fundamentally difficult one. Even I find I won't say what it is, but there's a math YouTube channel that I like, and the guy did a really nice series on the calculus from a geometrical standpoint, like what we had with the circle and the verse sign on Wednesday. It's very nice. But then when it came down to talking about what happens at the moment, change, he said, yeah, but there is no such thing as change. What's real are the moments. And then how the moments, a difference between the moments as opposed to a difference making the moments. This guy, I think I'm going to give him a little bit. It's shocking to me. It was like, wait, where did that come from? And it was actually, we didn't read it in this earlier quote from Lynn, but he's saying what you're supposed to say, according to how he, his mathematical tradition and so forth. So Julian, is the complex domain actually a physical thing, or does it just have physical effects? Yes, it is real. So maybe physical, it depends on what you mean by physical, as as physical causes. Yes, I mean, is gravity real, or is only the position of a planet or a falling rock real? The gravity, the cause, is real. And so the complex domain is saying, hey, reality has got to include what makes things happen, not just the things that we observe. The real numbers are, you can analogize to observations, things you can see. The whole rest of the complex domain. Yeah, Julian, go ahead.
Yeah, just scrolling up, just two from the chat line. The first question was, is it the complex domain like gravity in the sense we don't ever see gravity with our eyes, we're seeing it with our mind. So are we seeing, can you see this complex domain with your eyes per se, like in some, empiricist thing, like you're just, okay, sense perception, or is it only you got to hypothesize the complex domain like gravity? We never see gravity with our eyes, we're seeing it with our mind. Is a complex domain the same thing like that? You've seen it only with your mind?
Well, okay. Let me respond to that from Leibniz and from Gauss. So with Leibniz, the cause of change, the differential, was able to really be brought into the same language with its effects. You could write a mathematical expression that includes both the actual, the observable outcome and the cause behind it. Gauss dealt with the complex domain in a way that made it physical, made it visible. We saw those, didn't really explain them, but those green and red curvy things with the blue plane, that was Gauss's visualization of the complex domain. So before him, square root of -1 was just a symbol. With Gauss, it became something physical, which I encourage everyone to tune in on Wednesday for. And then let's see here, two other questions. Richard Burden's or comments. There are more square roots than fractions because every fraction is also a square root of its square, which is another fraction or a whole number, but not every square root is a fraction. It depends, Richard, on whether you're saying there are more square roots of fractions than there are fractions. It's a little imprecise what you've written. So if you're saying the square root of fractions and then the number of fractions, no, that's the same number. Because you could have a book where the page number is the fraction and written on the page is the square root of that fraction. You'd have the same number of pages of both. Denise asks, is this the complex domain? Yes. Okay. let's continue. I think we have online reader now. And we're going to be reading, it's on the last excerpt on page 8. I'll pull it up here. If you would like to speak, please raise your hand or just unmute.
We can do it if you want.
Well, Jose, if you got, please do.
From right there, right? The central feature?
You got it.
The central feature of my original contribution to the Leibniz science of physical economy is the provision of a method for addressing the causal relationship between, on the one side, individuals' contributions to axiomatically revolutionary advances in scientific and analogous forms of knowledge, and, on the other side, consequent increases in the potential population density of corresponding societies. In its application to political economy, my method focuses analysis upon the central role of the following three-step sequence. First, axiomatically revolutionary forms of scientific and analogous discovery. Second, consequent advances in machine tool and analogous principles. Finally, consequent advances in the productive powers of labor. These discoveries were initially the outgrowth of 1848 to 1952 objections to the inappropriateness of Norbert Wiener's application of statistical information theory to describing both the characteristic distinctions of living processes and of communication of ideas. I countered with a contrary, non-statistical definition of negentropy, as that meaning of the term might be derived from the common, physically distinguishing characteristic of an evolutionary biosphere. This non-statistical counter-definition of negentropy was then stated in terms of a successfully self-developing physical economy. The efficient impact of scientific discoveries communication within such a negentropic physical economic process was treated as most typical of the communication of ideas in general. That was the initial core of my discovery, up to the year 1952. Yet up to that point, the appropriate mathematical representation of such a form of physical economic negentropy was still wanted. The third step, taken through an intensive 1952 study of George Cantor's 1897 Beiträge, opened the doors of the transfinite domain upon a fresh insight into the relevant features of Bernhard Riemann's contributions. Thence, the applied form of my definition of physical economic negentropy acquired the title of LaRouche-Riemann method. My 1950 Oh, sorry, go ahead.
No, I was going to say, please continue.
My 1952 study of Cantor's Beiträge, am I pronouncing that right?
Beiträge.
I have no idea what someone just said, so I'm going to keep the way I'm doing it. It just sounds okay, whatever.
Beiträge.
Thank you. Beiträge provided the key to developing this conception further. Following that study, later the same year, I was electrified by rereading the relevant, most crucial passage of Riemann's habilitation dissertation, applying the Cantorian implications of my own notion of negentropy to Riemann's stated crucial problem of a continuous manifold, sent sparks flying in all directions. Cantor's transfinite was key to bringing my two elements together in this way, my own and Riemann's. This combined view of the universe of physical economy's experience, seen as a functional continuum, guided me to construct revisions in the applicable theory of knowledge, to exclude all residues of sense certainty's notion of linear ontological elementarity, and to replace these entirely by the elementarity of universal negentropically evolutionary change in Heraclitus's and Plato's sense of the ontological elementarity of nothing but change. This required that the popular idea of a mathematical certainty must be put aside to be superseded by a corrected view of the theory of knowledge. No system of deductive contemplation of our sense experience can be human knowledge. We know the universe only to the degree we surpass sense certainty by reflection upon the willful means through which we increase man's power over our universe.
Yeah. Our ability to act on the universe, if you're trying to understand what are the principles that underlie the universe, what makes things happen, if you leave out human beings, you're very incomplete. So let's just continue. Let's read Riemann. Let's see if the sparks are flying. Let's see if the clear idea of the connection to Platonic hypothesis comes across. And I believe we are due for an in-room reader. So we'll have someone read the whole opening part of the investigation.
I will. I already read, but I would love to read it if no one else is volunteering.
Go ahead.
Is Lynn volunteering?
No,
Okay.
Or I thought he asked for online.
No, he said in room.
Okay, Diane, and then what?
Okay. Tell me where to stop. All right, Bernhard Riemann on the hypotheses which lie at the foundations of geometry, 1854. Translated by Henry White from Vassar College in Poughkeepsie, New York. Yay. Plan of the investigation. It is well known that geometry presupposes not only the concept of space, but also the first fundamental notions for constructions in space as given in advance. It gives only nominal definitions for them, while the essential means of determining them appear in the form of axioms. The relation of these presuppositions is left in the dark. One sees neither whether and in how far their connection is necessary, nor a priori whether it is possible. From Euclid to Legendre, to name the most renowned of modern writers on geometry, this darkness has been lifted neither by the mathematicians nor by the philosophers who have labored upon it. The reason of this lay perhaps in the fact that the general concept of multiply extended magnitudes, in which spatial magnitudes are comprehended, has not been elaborated at all. Accordingly, I have proposed to myself, at first, the problem of constructing the concept of a multiply extended magnitude out of general notions of quantity. From this, it will result that a multiply extended magnitude is susceptible of various metric relations, and that space accordingly constitutes only a particular case of a triply extended magnitude. A necessary sequel of this is that the propositions of geometry are not derivable from general concepts of quantity, but that those properties by which space is distinguished from other conceivable triply extended magnitudes can be gathered only from experience.
Let's talk for a moment here. I heard various mutterings. Would anyone like to give voice to their thoughts so far?
Well, the first thing that comes to mind to me is thinking of Lynn's criticism of Euclidean geometry, starting with arbitrary axiomatic bases, this notion of the arbitrary point and straight line, and what you learn in school about how to manipulate those things on a piece of paper on a flat surface, versus the idea that he always posed that geometry is physical and it exists in real space. That it has to have from his observation. So anyway, it may be kind of a loose, but that's sort of what I was thinking, is that he's saying you have to derive geometry from physical experience as it exists. One thing I remember I picked up somewhere was the idea that the Pythagorean theorem was something originally developed by the Egyptians as a physical way of restoring the boundaries of the fields when the Nile would flood and would wash out those boundaries. That they developed this method using ropes to reconstruct the boundaries of the fields as a physical, as opposed to a. I think he's getting at something more fundamental.
Okay, and make sure that what you're about to bring up is in the text that we read so far, because be mindful that many people online have never read this. So try to make sure your comments aren't about the ending of this paper or something.
No. He's saying even assuming something about geometry or even physical space means you have to have a concept of magnitude, quantity before you have any other idea about it. I don't know.
That sounds like he's saying that's what they're saying.
Okay.
Isn't that it sounds to, maybe I'm not understanding, that they're saying that you can only understand it if you understand quantifiable magnitude, but it seems to me that he's implying there's something more than that. It's a principle of, I mean, I'm just thinking myself, we take for granted, if you say 3 dimensions, you immediately have in your mind this little 3-dimensional thing. Why do we assume that's the only way that space can be organized?
Yeah, if you imagine, so from the first sentence, geometry presupposes not only the concept of space, what is presupposed about that concept of space? What assumptions are made about space from school on? What specifically do we take for granted?
That's, for example, that straight line exists.
Well, how about so the straight lines
Relationship between things.
Well, that it's up, down, side. I mean, that you can sort of
Cartesian.
map everything in this.
X, Y, and Z axis kind of division of everything.
Yeah, well, imagine that we lived on let's say that, we live in 3 dimensions. Let's say we lived on 2. Let's say we lived on a surface and we were flat little creatures, like in the book Flatland. We might assume that space is flat. Maybe it isn't. Maybe it's curved. It's hard even for us to think about whether 3-dimensional space is curved, because we can't stand outside of it. But one of the biggest assumptions is that space is flat. Here's a very specific one. He says the first fundamental notions for constructions in space are given in advance. You brought up the infinite line, straight line. If there are 2 lines that are parallel, will they never reach each other? You go forever. Has anyone ever gone out to forever to find out? So this is something it seems plausible, but you don't really know if it has to be true. Is that true about our universe or just an imaginary one? Let me respond to a few things from the chat, and then we can read a little bit more. Question was, is the focus on math by Lyndon because he knew numbers is the communication of aliens and the golden ratio math? No. LaRouche did not believe himself to be in communication with extraterrestrial life. Ron says, perhaps a reference to a visual previously used may be helpful in visualizing the complex domain. The visual shows randomly appearing, seemingly arbitrary dots of light, although not arbitrary at all when viewed from the 3rd dimension, as the projections down from the intersections of 2 rotating spirals. Well, sounds like we could talk after this and figure out how to make that. Susan points out that we learned that space is empty. Remember, that was Newton's view. Space is already here and it's empty. And it's flat. Newton assumed it was flat. Denise says, creative mentation changes the universe. The mind can move a mountain or go to the moon, so the unseen is reality. Creative insight is a physical change. Richard Burden, would space still exist if there were no objects or material in it, or if the material were absolutely uniform? And Richard's hand is up too. Would you like to say something, Richard?
Oh, well, that's basically what I was going to raise. I don't have anything else to say.
Okay. let's keep that as a question for now, and let's see where it goes. That question again, would space still exist if there were no objects or material in it, or if the material were absolutely uniform?
Hard to imagine. It's certainly hard to imagine.
Eugene, yes, briefly, and then we'll keep reading. Eugene, you got your hand up?
Yeah, sorry, do you hear me?
Yes.
Oh, sorry. I think what he's trying to say is that science is a work in progress, and we have to continue with getting out different types of ideas, and some of them might be wrong, some of them might be right, but we have to continue pursuing different options, and that's probably why the Chinese, that they don't have as many dogmas as we have in the Western world, have been able to come out with this improvement in technology where they're ahead of the West in most of the fields. And that has to do with that everything is out there, but science hasn't proved it. So some of the things that are out there, we just need to prove them in a scientific way, but they do exist. The problem is we haven't been able to see them because as humans, we have a certain spectrum of things that we can see, of things that we can listen, and there are things that we as humans cannot understand because they're out of reach.
Okay, all right, well, let's keep, I mean, there's many things that we don't sense that are not out of our reach. I know that's not what you're saying, but that's what I'm saying. All right, let's keep reading what Riemann has to say. And, well, Diane, why don't you just continue?
Okay.
It arises from this.
There arises from this the problem of searching out the simplest facts by which the metric relations of space can be determined, a problem which in the nature of things is not quite definite. For several systems of simple facts can be stated which would suffice for determining the metric relations of space. The most important for present purposes is that laid down for foundations by Euclid. These facts are, like all facts, not necessary, but of a merely empirical certainty. They are hypotheses. One may therefore inquire into their probability, which is truly very great within the bounds of observation, and thereafter decide concerning the admissibility of protracting them outside the limits of observation, not only toward the immeasurably large, but also toward the immeasurably small.
Okay, let's keep reading. So let's go to an online reader for section 1. I get a volunteer from Zoom, please.
I'll volunteer.
Okay, go ahead.
Okay, great. So the concept of an n-fold extended manifold. While I now attempt in the first place to solve the first of these problems, the development of the concept of manifolds multiply extended, I think myself the more entitled to ask considerate judgment inasmuch as I have had a little practice in such matters of a philosophical nature, where the difficulty lies more in the concept than in the construction. And because I have not been able to make use of any preliminary studies whatever, aside from some very brief hints, which Privy Councillor Gauss has given on the subject in his second essay on biquadratic residues, and in his Jubilee booklet, and some philosophical investigations of Herbart. Shall I continue?
Yes.
Notions of quantity are possible only where there exists already a general concept which allows various modes of determination. According as there is or is not found among these modes of determination a continuous transition from one to another, they form a continuous or a discrete manifold. The individual modes are called in the first case points, and in the latter case, elements of the manifold. Concepts whose modes of determination form a discrete manifold are so numerous that for things arbitrarily given, there can always be found a concept, at least in the more highly developed languages, under which they are comprehended. And mathematicians have been able, therefore, in the doctrine of discrete quantity, to set out without scruple from the postulate that given things are to be considered as all of one kind. And on the other hand, there are in common life only such infrequent occasions to form concepts whose modes of determination form a continuous manifold, that the positions of objects of sense and the colors are probably the only simple notions whose modes of determination form a multiply extended manifold. More frequent occasion for the birth and development of these notions is first found in higher mathematics.
Okay, a moment now for, he had raised the distinction between continuous and discrete. And he said that among continuous multiply extended magnitudes, the only examples he said that came up were space, positions of objects in space, and the colors. Let's, what does he mean by this? What's first off, let's think of a few concepts that have multiple specifications. For example, length is one concept, and it has multiple specific examples of length, 2 inches, 3 feet, whatever. Is length continuous? Is it discrete? Between two lengths, is there always another one in between?
Sure.
Yeah.
If so, let's consider it continuous. It doesn't jump. So let's think of, can anyone think of an example of a discrete manifold? Something that we measure, when we measure it, we have specific jumps. It's not smooth in between.
Piano keyboard.
Piano keyboard. Yep.
The number of people.
A number of people. Yeah. The attendees in a Zoom room, for example. You don't get, you don't have a half a person. Well, yeah, right.
Depends how much coffee we have.
Okay, so counting up the numbers of people, keys on a piano keyboard, these are discrete. And then length or distance maybe is a continuous one. Let's come up with 2 more examples of continuous manifolds. What's something else we measure?
I'm trying to understand why
Temperature.
he says
Temperature.
objects in space are continuous. Isn't that what he said?
No,
I'm
no,
not
no,
reading it.
careful.
Okay.
Read that. What does he say is continuous? Look at that
To
phrase.
form a continuous map that the positions of objects of sense.
The position.
Okay, the position.
Yeah,
Oh,
the
okay.
location is continuous.
I see. Okay.
Art pointed out that temperature is continuous. Any other example, continuous or discrete manifold?
Well, the human mind is a continuous manifold.
One person's maybe. Or is it in general?
Well, in your film, which I saw at the beginning of the cello string, the tones in the cello string are continuous as opposed to a keyboard.
Okay, how about a trombone? And you go, is it possible to play a note that doesn't exist on a trombone, or does it jump?
Oh, no, you can do it.
Oh.
Yeah.
There's an upper and lower limit though, so it's limited.
Yeah,
They
it's-
have
it's
boundaries.
continuous.
Just like the length of a string has.
Stason says the universe is a continuous manifold symbol of discontinuity. All right.
A question.
Yes.
His use of the word manifold, he's using it in 1854. So was that as far as you know, is that something, a word that was used at that time? Because I think of, not that I know that much, but I think of the use of the word manifold is he's thinking as a generalized geometric object. So it's a much more general concept than, talking about specific shapes. He's getting away from the polyhedron and stuff like that. And manifold is talking about something that's more generalized. Is that how you think of it? Is that how he was thinking of it?
Yeah, I
And
think so.
Was that a term that was used at that time?
I don't know how the term was used in his period. He doesn't, it's just from his writing, it doesn't seem like he's expecting this to be a surprising term.
He does say that these concepts are accessible to more highly developed languages. You know,
What did he say about highly developed languages?
concepts whose modes of determination from a discrete manifold are so numerous that things arbitrarily given can only be found a concept, at least in the more highly developed languages under which they are comprehended. In other words, you're asking about the use of the term manifold. He's obviously talking about people who have a better, higher developed language.
That's not what he's saying.
No?
No.
Okay.
But let's look at that sentence. Concepts whose mode of determination form a discrete manifold are so numerous that for things arbitrarily given. Let's arbitrarily give three things. Pencil. Okay. Mike's pencil. What else?
Cup.
Art's cup. And a third thing, please.
Glasses.
The glasses. In our highly developed language, is there something that you can say that would indicate that you're talking about those three things?
For sure.
Go for it. How would you say it?
Mike's pencil, my cup, and Jeff's glasses.
Okay.
Maybe we weren't arbitrary enough because these are all things on the table.
Well, that's all Riemann's saying there. Riemann is just saying that if you have a collection of things, you can treat that as one concept, and language that's developed is able to find some way of that's all he says there.
Okay.
Okay, let's keep going. And Margaret, why don't you continue? And then I saw Joe had put his hand up also. So you can be in the queue.
Okay.
Margaret, go for it.
All right. Determinate parts of a manifold, distinguished by a mark or a boundary, are called quanta. Their comparison as to quantity comes in discrete magnitudes by counting, in continuous magnitude by measurement. Measuring consists in superposition of the magnitudes to be compared. For measurement, there is requisite some means of carrying forward one magnitude as a measure for the other. In default of this, one can compare two magnitudes only when the one is a part of the other, and even then, one can only decide on the question of more or less, not upon the question of how many. The investigations which can be set on foot about them in this case form a general part of the doctrine of quantity independent of metrical determinations, where magnitudes are thought of not as existing independent of position and not as expressible by a unit, but only as regions in a manifold. Such inquiries have become a necessity for several parts of mathematics, namely for the treatment of many-valued analytic functions, and the lack of them is likely a principal reason why the celebrated theorem of Abel and the contributions of Lagrange, Foss, and Jacobi to the theory of differential equations have remained so long unfruitful. For the present purpose, it will be sufficient to bring forward conspicuously 2 points out of this general part of the doctrine of extended magnitudes, wherein nothing further is assumed than what was already contained in the concept of it. The first of these will make plain how the notion of a multiply extended manifold came to exist, and the second, the reference of the determination of place in a given manifold to determinations of quantity and the essential mark of an n-fold extension.
Okay. Let's just keep going. As always, raise your hand or type in the chat if you'd like to say something. I want to make sure we get to the thrilling finale. So I think
that last 4 or 5 sentences, do you have an illustration of what he's talking about?
4 or 5 sentences.
Let's say for the present.
For the present purpose, it will be sufficient to bring forward conspicuously 2 points out of this general part. Is that what he's getting to right now?
Yeah, so the first part is what's going to be in the next section. You know, what
Okay.
is a multiply extended manifold? And then in section 2, which we are not fully going to read, he's going to, and then in part 3 here, he's going to talk about how do you determine location in a multiply extended manifold.
Okay.
Segue to the next section. Okay, in-person reader, please. Number 2.
I can do it.
Before, let's yeah, bring the microphone. Right, here we go.
In a concept whose various modes of determination form a continuous manifold, one passes in a definite way from one mode of determination to another. The modes of determination which are traversed constitute a simply extended manifold, and its essential mark is this: that it is in a continuous progress, is possible from any point only in 2 directions, forward or backward. If now one forms the thought of this manifold again passing over into another entirely different, here again is a definite way, that is, in such a way that every point goes over into a definite point of the other. Then will all the modes of determination thus obtained form a doubly extended manifold. In similar procedure, one obtains a triply extended manifold when one represents to oneself that a double extension passes over in a definite way into one entirely different, and it is easy to see how one can prolong this construction indefinitely. If one considers his object of thought as variable instead of regarding the concept as determinable, then this construction can be characterized as a synthesis of a variability of n+1 dimensions out of a variability of n dimensions and a variability of 1 dimension.
Let's talk about how multiply extended a manifold is. Riemann says that in a simply extended manifold, progress is only possible in 2 directions, forward or backward. So let's think back to some of those examples that we gave of these. So we had temperature, we had piano keys, we had length. What were the other simply extended ones? Well, maybe let's go with those. So temperature. If you have a certain temperature, how many different ways can you change that temperature? 2. You can go up or down. How about distance? How many ways can you change distance?
Forward and backward.
Forward and backward. Piano key. Go up.
Down.
You can go down. So that's what Riemann is saying. If you can only change, if you've got some concept and you can only change from one specific instance of that concept to another, from one length to another, if the only kind of change is in 2 directions, it's simply extended. So this line, for example, is simply extended. He says, if you then imagine your whole manifold moving into another one, but in a specific way, like each point from the lower line turns into its corresponding point in the upper line. And if you could keep doing this, moving this line back and forward, you'd be making a doubly extended manifold, some kind of a surface. And you're seeing if you then added a third kind of action to it, you could have a triply extended manifold. Now, how many ways, let's say we're on a surface, we're on this whiteboard. So unlike temperature, where we can get hotter or colder, how many ways can we move from this spot on the whiteboard? Anyway, we can't move this way. We're on the whiteboard, so Yeah. We can move up or down. Is that the only way we can move? We can move left to right. You can move in any direction. Now, in this case, any direction, no matter what direction we're moving in, we could indicate that by giving two numbers. For example, we could say how far to the right and how far up. We give those two numbers, and that's a way of identifying a direction of moving within this doubly extended manifold. It's not just forward or backward. We've got sort of two independent kinds of change now. We're talking about positions on the whiteboard. And for positions in space, it's three. You have to give three things to say where you are in space, or color. Color is three-dimensional. He's talking about continuous manifolds here. Yes.
How is color three-dimensional?
Well, let's try to, very good question. Let's try to put the colors on, let's first try to put the colors on a line. Now, this is a really fun thing to do, is get yourself a box of crayons, serious, and then try to put them into some kind of, figure out how you would order them. So first off, let's say that we want to just put the crayons all in a row. So crayon, 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 crayon. So let's say it's one-dimensional. What is that one? I mean, we can't just say lighter and darker, right? That's not enough. But we could start with that, lighter and darker. So okay, that's one aspect of color. Yeah, so how do we describe the shading? How do we turn that into something, if not numerical, something that's continuously changing? What concept embodies different shading? Frequency. That's pretty good. What frequency is white light? Well, it corresponds to a high temperature, but it doesn't have a frequency. Yeah, white light has multiple frequencies that make it up. So like a laser, okay, you've got a pure, like a red or a green. Okay, what is the frequency of this laser? Yes, you could sort lasers by their frequency, but color doesn't work. White has many frequencies within it. Pardon me? Red, what about red? How red? Well, red light, it could look red to you. Unless it's made by a laser, it has more than one wavelength probably, or an LED.
From ultraviolet to infrared.
Yes, so that's frequency. So we could try to, organize the colors from ultraviolet to infrared. So let's
check out this chat. There's a number of interesting.
Or violet. Okay, let me take a look at the chat. Let's first say that then we'll try to see if this works. Okay, wavelength. Okay, same, basically the same as the inverse of frequency. The n-fold manifold sounds like the reality of Whittaker's n-folded electromagnetism with the longitudinal one. I'll have to get back to that. Compositions of three primary colors, spectrum of light. Okay, some good thoughts there. Oh, wrong mic apparently. Red, yellow, blue. Okay, so first let's take a look at the wavelength issue and see what we can make of this. Red through violet. Where on this is brown? If you take light and you put it through a prism and you see the spectrum, is brown on there?
How about magenta?
I think so.
Yeah.
Magenta there, or purple, like a pinkish.
So there are plenty of colors that are not on the, here's why. Because our eyes, see, it comes from our eyes. Our eyes are three-dimensional. I mean, triply extended in terms of how we sense light. We have three different kinds of cones in our eye. So you might say that we could say what color light is by how much it excites the three kinds of cones in the human eye. In that case, it's triply extended.
I know that there are some people which are like so they don't see the same color.
It's indeed, it's possible. You can have, see colors a little bit differently, or very differently.
Colorblind.
Being colorblind. So, for example, how about computer screens? How do computer screens make all these different colors? You ever look really close at one? Or maybe a TV when they're bigger? And
They're little pixels.
They have little dots.
Yeah, what color are those dots if you look real close?
RGB.
They're red, green, and blue. Yeah. Yep. So those three colors are used to make the appearance of any color, and you can get pretty much any color on TV. Not all of them. They're not perfect. So anyways, that's why light is not it's not just intensity and wavelength, because magenta, see our eyes, what happens if your cone that's on the red side and your cone on the purple side are both being stimulated, but not the green one in the middle? Well, the mind has to come up with some way of interpreting that, and that's magenta. It's sort of in between the red and the violet. So yeah, so it's not just a way of a simple spectrum. The number of dimensions of color depends on what kind of animal is looking at it. That is true. Most birds have 4 cones, or so they see color differently than we do. Okay. I think that's good. Oh, now for the 3 dimensions of color, you can say, okay, let's break it down into 2. Let's say I've got,
common way it's done is hue, saturation, and brightness. Hue is, it's like wavelength, except it includes magenta.
Jason, your mic just shifted for
Okay.
some unknown. Yeah, that's
You can hear me? Okay. So the one way
no,
is hue.
no. Sorry.
Yeah, okay, it might be you. If someone else is having issue, please also speak up.
We can't listen, Jason. We don't listen right.
You can't hear me. Okay.
I think it switched from your lapel mic to the room mic.
Well, you're not hearing the tapping?
No, there's no tapping.
No, maybe.
We'll use this other mic then. Who knows? Okay, so actually, we've talked enough about color. Let's keep moving. I think it's really interesting, but we could talk about any of these parts for a great deal.
Okay, I agree, but what were the 3 things? Hue, saturation, and what?
Well, there aren't 3 things. So one example, one way of doing it with 3 things is hue, saturation, and intensity, or luminosity.
Right.
So where on the hue color wheel are you? How saturated is that color? In other words, do you have like a really nice green, or is it kind of grayed out and not very intense kind of green? Did you take kind of the color out of it? It's becoming more black and white. And then also, how bright is it? Those are 3. That's one way. Another way for computers is how much red, how much green, how much blue. So light is 3-dimensional, color, not light, color is 3-dimensional that way. There's another one called LAB color, which I'm not going to say exactly what that is, but it also uses 3 dimensions. So color is triply extended, but what those extensions are is not fixed. You can pick different ways of doing that. Just like, even though a surface may be doubly extended, there's multiple different ways of saying where a location is. You could say how far to the right and how far up. Or you could say, we're going to fly there. What's our heading? And what's our distance? So what are the 2 dimensions of space? Is it X and Y? Or is it direction and distance. They're both fine, but they're both irreducibly doubly extended. You have to say two things to give a position on a surface, three in space. Okay, let's keep moving. Let's keep moving. If there's more thoughts, please, did we get to the end of?
Yeah, we did.
Yeah,
Let's got to three. Okay, so in that case, it's time for an online reader for part three. Joe, yeah, that's right. Joe was on deck, I believe. And I see Deborah Sonnenblick is, would you like to? And Richard Freeman are unmuted.
Actually, it's Elizabeth Jennings is volunteering, okay?
Okay.
And where are you?
Section 3 on page 11, please.
Okay. I shall now show how one can conversely split up a variability whose domain is given into a variability of one dimension and a variability of fewer dimensions. To this end, let one think of a variable portion of a manifold of one dimension, reckoning from a fixed starting point or origin, so that its values are comparable one with another, which has for every point of the given manifold a definite value changing continuously with that point, or in other words, let one assume within the given manifold a continuous function of place, and indeed a function such that it is not constant along any portion of this manifold. Every system of points in which the function has a constant value constitutes now a continuous manifold of fewer dimensions than that which was given. By changing the value of the function, these manifolds pass over one into another continuously. Hence, one may assume that from one of them all the rest emanate, and this will come about, speaking generally, in such a way that every point of one passes over into a definite point of the other. Exceptional cases, and it is important to investigate them, can be left out of consideration here. By this means, the fixing of position in the given manifold is referred to the determination of one quantity and the fixing of position in a manifold of fewer dimensions. It is easy now to show that this latter has n-1 dimensions if the given manifold was n-fold extended. Hence, by repetition of this procedure to n times, the fixing of position is an n-dimensional in an n-dimensional manifold is reduced to n determinations of quantities, and therefore the fixing of position in a given manifold is reduced, whenever this is possible, to the determination of a finite number of quantities. There are, however, manifolds in which the fixing of position requires not a finite number, but either an infinite series or continuous manifold of determinations of quantity. Such manifolds are constituted, for example, by the possible determinations of a function for a given domain, the possible shapes of a figure in space, etc.
Okay, I think is there anything anyone desperately wants to say about that section? Or not? Or you don't have to be desperate.
I don't feel confident that I understand it.
Yeah, I don't understand that.
Okay.
No.
All right, let's give an example. So let's stick with, how about let's talk about position in space. This is a three-dimensional, a triply extended manifold. How do we break down what those three are? We're going to together come up with two different ways of talking about where something is in this room. Would anyone like to put forward a proposal of how we might do that?
Things above something or?
Okay. Above or below. So that's our first one. Height. Okay.
How much? I mean, there's a distance involved. Oh, well, you said that above or below, but
Okay, above or
wide and-
below, that tells us something. It's not
Right.
enough to locate something in this room. We're making a treasure map, right? It might be up on a shelf and, or, you know, we got to say where it is. So our height, that's part of it. Okay.
The
What
wide
else?
and the length,
Pardon me?
the wide and the length.
The width and the length.
Yes.
So maybe we could, if we start from this corner, you could say how far this way, how far this way, how far this way. So we broke down something that was triply extended into a specific way of saying what three things could we use to say where we are in it. It's not the only way. What's another way that we could say where something is in this room?
If you go from this corner down to this corner up,
And what else? Because not everything in the room is on this line.
oh, okay.
you could say in
the-
relation to something
I
else.
think I said something about it here. Can you say more of what you're thinking there?
So if you have a big sphere and say this room is in it, and wherever, let's say that polygon, you describe how far the distance is, and then what the rotational degree is, and maybe height.
Yeah, it's else. So you might start by, okay, how do I look at it? You might say, how do I look at that object? How far do I twist my body left or right? How far do I tilt my head or my eyes up or down? And how far away is the thing? So they're both ways of breaking up that triply extended manifold into three things. He says, instead of into n determinations of quantities, we get three numbers. Distance this way, x, y, z, or the three numbers might be, longitude, latitude, distance.
So n dimensions is n quantities or n metric.
It means that you need n specific determinations of these individual manifolds to give a location in the triple one, yeah, for the n-fold one. Yes.
I think it's very interesting that he says possible determinations of a function for a given domain. I'm thinking, if you consider the domain to be the interval from 0 to 1,
Mhm.
and you consider all the continuous functions on that interval, he's considering that to be a manifold. If I interpret that
Yeah.
correctly.
And
I find that fascinating.
And how many dimensions is that
Yeah, that's
manifold?
Yeah.
Right. So that's infinite. There's an infinite number of ways of varying. The same with light. Same with light. You break down light into you use a prism to break it out. Every frequency, you could measure how intense is the light at that frequency. There's an infinite number of these frequencies for you to make measurements at. To perfectly describe that light, if you're just doing it observationally and not thinking about what made it, you'd have to make a continuously infinite number of measurements. So compared to only three when you're talking about color as perceived by human beings. Light and color, very different. Okay, there's some, let's see here. Okay, so let's keep going. Are we in the room now, or I forget?
Yeah, Betty was reading on.
Oh yeah, that's right. Okay, so somebody in the room here for part 2, which you'll see ends with an ellipsis. We're not going to read all of it.
I'll read it.
Okay, was there anyone, have you read yet?
No.
Oh, you didn't? Okay.
Part 2, relations of measure of which an n-dimensional manifold is susceptible on the assumption that lines possess a length independent of their position. That is, that every line can be measured by every other. Okay. Now that the concept of an n-fold extended manifold has been constructed, and its essential mark has been found to be this, that the determination of position therein can be referred to n determinations of magnitude. There follows a second of the problems proposed above, an investigation into the relations of measure such that a manifold is susceptible of, also into the conditions which suffice for determining these metric relations. These relations of measure can be investigated only in abstract notions of magnitude and can be exhibited connectedly only in formulae. Upon certain assumptions, however, one is able to resolve them into relations which are separately capable of being represented geometrically, and by this means it becomes possible to express geometrically the results of the calculation. Therefore, if one is to reach solid ground, an abstract investigation in formulae is indeed unavoidable, but its results will allow an exhibition in the clothing of geometry. For both parts of the foundations are contained in the celebrated treatise of Privy Councillor Gauss upon curved surfaces.
Let's just keep going. Oh, Privy Councillor Gauss on curved surfaces. Okay, this I will mention. This is really very fun. Carl Gauss in 1820s, I think, wrote this really phenomenal paper about curved surfaces, surfaces in general. And in it, he solves that question that we had talked about earlier, which is that if we were flat two-dimensional creatures, how would we know that we live on a round Earth as opposed to a flat one? Gauss comes up with several ways of answering that, of just looking at measurements inside your manifold to figure out the relation between the different ways of moving within it. Riemann is saying, let's apply that to space. We can't step out and look at space from the fourth dimension, but we can, using a method very much like what Gauss did for general surfaces, we could come up with a general theory of curved spaces, of curved four-dimensional manifolds, of curved five-dimensional manifolds. So this gets to that question, the actual space that we live in, which of the infinite variety of curved spaces is it? Okay, let's keep going. Online reader, please, for section 3, part 1, application to space. Let's see, Marty on the chat says make a floor plan in 3 dimensions. As an example of, you know, the 3. Where are you on that level of the house, and then which level are you on the house? The way of dividing up 3 dimensions. Hey, online reader, please.
I volunteer.
Yes. Okay.
Following these investigations concerning the mode of fixing metric relations in an n-fold extended magnitude, the conditions can now be stated which are sufficient and necessary for determining metric relations in space, when it is assumed in advance that lines are independent of position and that the linear element is representable by the square root of a differential expression of the second degree. That is, if flatness in smallest parts is assumed. These conditions in the first place can be expressed thus: that the measure of the curvature in every point is equal to 0 in 3 directions of surface, and therefore the metric relations of the space are determined when the sum of the angles in a triangle is everywhere equal to 2 right angles. In the second place, if one assumes at the start, like Euclid, an existence independent of situation not only for lines but also for bodies, then it follows that the measure of curvature is everywhere constant, and then the sum of the angles in all triangles is determined as soon as it is fixed for one triangle. In the third place, finally, instead of assuming the length of lines to be independent of place and direction, one might even assume their length and direction to be independent of place. Has he just restated what he said a minute ago? I don't get that. In the third place, and finally, instead of assuming the length of lines to be independent of place and direction, one might even assume their length and direction to be independent of place. Upon this understanding, the changes in place or differences in position are complex quantities expressible in three independent units.
Let's take a deeper look at these three possibilities that he gives here. So let's start with the first paragraph. These conditions in the first place can be expressed thus. The measure of curvature is 0 everywhere. Sum of angles in a triangle is equal to 2 right angles. This is Euclidean geometry. This is flat geometry. But then get this zinger. In part 2, he says, in the second place, if we assume, like Euclid, an existence independent of situation, not only for lines, but also for bodies. What that means is, if you move something around, it doesn't change just as the result of you moving it around. It has its position doesn't affect what it is at all. And he says, okay, well, if that's true, then the measure of curvature must be everywhere constant. Not necessarily 0, just constant. And the sum of the angles in all triangles is determined as soon as it is fixed for one triangle. Imagine living on a sphere. If you're in a perfect sphere and you take any shape on it, and you cut it out, you could move it all over the sphere and it'll fit perfectly. So it always has the same curvature, there's no problem. If all of a sudden, if it was more like an egg, and you brought it to the pointy end, you'd have to kind of squish it, or the object itself would have to change somehow to be able to exist in that part of it. So if moving things around doesn't change them, then the curvature has to be the same everywhere.
Like looking at a curved mirror and it distorts the image on the surface of the mirror.
Yeah, a curved mirror would distort the image.
That's like holding a shape on a curved surface, right? It's sort of the same effect.
Yeah, if it's changing.
Well, like on a sphere, any triangle would have greater than 180 degrees, more or less, right?
Yeah. If like you imagine being on that sphere, triangles always have more than 180 degrees.
But they wouldn't be uniform unless they were the same size, I think.
Right. The excess above 180 right angles is based on the size of the triangle on a sphere. That's true. Okay. Michael, how can we determine the 3D shape of the space we live in? We're immersed in it, and not just the surface we are moving on. Good question. Let's see how Riemann treats this, and let's come back to it at the end if we're not satisfied with how he treated it. Okay, so we got the second case. First place, flat. Second case, constant curvature. Third place, anything goes. He says there'll be 3 independent units for, he's talking about space. So, you know what, actually, the measure of curvature of space itself is triply extended. At every point, the way that it's curved, you have to give 3 numbers to say how it's curved at that point. Unlike a surface where 1 number at each point tells you how curved it is. Okay, see the video. All right, so, okay. In-person reader for part 2, please. Sure, Margaret, go ahead. Do you mind?
No, I sort of lost this page.
Yeah, you got it.
In the course of preceding discussions, in the first place, relations of extension or of domain were distinguished from those of measurement. And it was found that different relations of measure were conceivable along with identical relations of extension. Then were sought systems of simple determinations of measure by means of which the metric relations of space are completely determined and of which all theorems about such relations are a necessary consequence. It remains now to examine the question how, in what degree, and to what extent these assumptions are guaranteed by experience. In this connection, there subsists an essential difference between mere relations of extension and those of measurement. In the former, where the possible cases form a discrete manifold, the declarations of experience are indeed never quite sure, but they are not lacking in exactness. While in the latter, where possible cases form a continuum, every determination based on experience remains always inexact, be the probability that it is nearly correct ever so great. This antithesis becomes important when these empirical determinations are extended beyond the limits of observation into the immeasurably great and the immeasurably small. For the second kind of relations obviously might become ever more inexact beyond the bounds of observation, but not so the first kind. Should I keep going? When constructions in space are extended into the immeasurably great, the unlimitedness must be distinguished from infiniteness. The one belongs to relations of extension, the other to those of measure. That space is an unlimited triply extended manifold. That space is an unlimited triply extended manifold is an assumption applied in every conception of the external world. By it, at every moment, the domain of real perceptions is supplemented, and the possible locations of an object that is sought for are constructed, and in these applications, the assumption is continually being verified. The unlimitedness of space has therefore a greater certainty empirically than any experience of the external. From this, however, follows in no wise its infiniteness, but on the contrary, space would necessarily be finite if one assumes that bodies are independent of situation and so ascribes to space a constant measure of curvature, provided this measure of curvature had any positive value, however small. If one were to prolong the elements of direction that lie in any element of surface into shortest lines, geodesics, one would obtain an unlimited surface with constant positive measure of curvature, consequently a surface which would take on, in a triply extended manifold, the form of a spherical surface, and would therefore be finite.
Maybe just to say a bit about this one. So he talked about the difference between extension and measure. So how about space? The fact that it seems that we can go in any direction without hitting a wall, is that about extension? Is that about measure? Does that tell us that motion in space is unlimited or that space is infinite? Well, how about this? We're on the ocean, we're on a ship, and there's no continents, it's just water. We can keep sailing around. We're never going to hit a wall, but is the planet that we're on infinite? So he's saying, okay, just because something's unlimited in terms of what you can do in it, doesn't mean it's infinite, because you might actually be looping back on yourself and not realizing it. So he comes back to this thing that if the measure of curvature in all of space is a constant, then if it was the slightest bit positive, space itself would be like a big sphere. And you would end up coming back on yourself if you went, billions of light years or whatever. Okay, let's press on. Let's press on. And aren't those mirror statements? Can you say more, Sarah, about what you mean there?
I think you might have just clarified it, but when I heard you say like, okay, on the one hand, if you can extend infinitely, and then is the space that you're in infinite, for some reason it sounded like those were just saying the same thing. But I think what you just said is no, they're not, but I don't really understand what you mean. Sorry.
Okay. Well, the words Riemann is contrasting here is unlimited and infinite. So unlimited, like this ship going around this ocean world, there's no a limit, like it's like a wall that you hit. Right? The ship's never going to hit a wall as it's circling around this planet again and again and again. But just because you don't hit a wall doesn't mean that the space that you're in, this ocean surface, is infinite. It's a finite size. It's based on the size of that planet. So he says, motion or extension could be unlimited without the world that you're doing that extension in being infinite.
Okay, thank you. I think that makes sense.
Okay. Anything else before we move on to the thrilling conclusion? All right. So let's go online for our last reader, or at least the first part of this last reader. Feel free to raise your hand if you've spoken today, but not if you have read already today. Any volunteer? Oh, someone's clapping again. I have to find out who this is. Joe, are you trying to raise your hand?
Well, I'm raising my hand, but clapping for your wonderful explication. So,
well, thank you. Thank
and
you.
everyone else should clap too. Where are we, Jason?
We're on the right column of page 12, section 3. Questions concerning the immeasurably large.
Okay, questions concerning the immeasurably large are, for the explanation of nature, useless.
Hey, thanks for the claps. Joe, you inspired a couple of other claps. Thank you.
Okay, great.
Sorry, go ahead.
Also, the hearts and smiley faces and all that too, right? Okay, questions concerning the immeasurably large are, for the explanation of nature, useless questions. Quite otherwise is it, however, with questions concerning the immeasurably small. Knowledge of the causal connection of phenomena is based essentially upon the precision with which we follow them down into the infinitely small. The progress of recent centuries in knowledge of the mechanism of nature has come about almost solely by the exactness of the synthesis rendered possible by the invention of the infinitesimal calculus and by the simple fundamental concepts devised by Archimedes, Galileo, and Newton, and effectively employed by modern physics. In the natural sciences, however, where simple fundamental concepts are still lacking for such synthesis, one pursues phenomena into the spatially small in order to perceive causal connections, just as far as the microscope permits. Questions concerning spatial relations of measure in the indefinitely small are therefore not useless. If one premise that bodies exist independently of position, then the measure of curvature is everywhere constant, then from astronomical measurements, it follows that it cannot differ from zero. At any rate, its reciprocal value would have to be a surface in comparison with which the region accessible to our telescopes would vanish. If, however, bodies have no such non-dependence upon position, then one cannot conclude two relations of measure in the indefinitely small from those in the large. In that case, the curvature can have at every point arbitrary values in three directions, provided only the total curvature of every metric portion of space be not appreciably different from zero. Even greater complications may arise in case the line element is not representable, as it has been premised by the square root of a differential expression of the second degree. Now, however, the empirical notions on which spatial measurements are based appear to lose their validity when applied to the indefinitely small, namely the concept of a fixed body and that of a light ray. Accordingly, it is entirely conceivable that in the indefinitely small, the spatial relations of size are not in accord with the postulates of geometry, and one would indeed be forced to this assumption as soon as it would permit a simpler explanation of the phenomena.
Let me pause you there, Joe. So this last thing that he's saying it's possible that when you look really small, space is curved in a way that for, like, larger pieces of space, it's basically flat. But if you drill down far enough, you'll see it's not. Then he brings up a light ray in this context. And to me, I just sort of hear this as being like prefiguring where Planck ends up going. Actually, I don't want to say more about that, so I shouldn't have even said that. Let's keep reading, Joe.
The question of the validity of the postulates of geometry in the indefinitely small is involved in the question concerning the ultimate basis of relations of size and space. In connection with this question, which may well be assigned to the philosophy of space, the above remark is applicable, namely that while in a discrete manifold the principle of metric relations is implicit in the notion of this manifold, it must come from somewhere else in the case of a continuous manifold. Either then, the actual things forming the groundwork of a space must constitute a discrete manifold, or else the basis of metric relations must be sought for outside that actuality in colligating forces that operate upon it. A decision upon these questions can be found only by starting from the structure of phenomena that has been approved in experience hitherto, for which Newton laid the foundation, and by modifying this structure gradually under the compulsion of facts which it cannot explain. Such investigations as start out like this present one from general notions can promote only the purpose that this task shall not be hindered by too restricted conceptions, and that progress in perceiving the connection of things shall not be obstructed by the prejudices of tradition. This path leads out into the domain of another science, into the realm of physics, into which the nature of this present occasion forbids us to penetrate.
Let me go back to one line a little earlier on this page. Joe, could you read this highlighted section one more time?
Namely, that while in a discrete manifold, the principle of metric relations is implicit in the notion of this manifold, it must come from somewhere else in the case of a continuous manifold.
Let's dig into what this sentence means. So in a discrete manifold, the principle of metric relations is implicit in the notion of this manifold. It's a lot of words. What's an example of a discrete manifold that we could test out our ideas on for this. Number of people. So how do you measure, if someone asks you, how do you measure the number of people? You basically said, well, it's the number, you count the number of people. Like you have the way you make a measurement is implicit in, how about another discrete manifold? Margaret had brought up keys on a piano. Well, once you say which key on the piano, you basically said, okay, you have a piano and it has keys. So you've said how you make measurements if it's discrete. But then Riemann says that it must come from somewhere else in a continuous manifold. The basis of measurement isn't in the manifold itself. Where must it come from? He says this: the basic of metric relations must be sought outside that actuality in colligating forces that operate upon it. What does that mean?
Does someone want to look up colligating?
Tying together.
We're talking about color, right? The source of the color is outside what the color is, right? The source of light, which you don't see the color unless there's a source of light impinging on the color, causing you to therefore see it. I don't know.
We're talking about measuring the color, or
well, also about the curvature. So what gives space its shape? We don't see that answer in space.
I mean, as if you're on the sphere, which is continuous.
Yeah. Let me just pose one thing from the chat and then go to Rick. Sarah says, is he pointing to the Y? Like the sun determining the motion of the planets? Yeah, exactly right. That's what Riemann is doing. And hey, pointed out that we're going on a little late now. All right, let's hear from Rick.
Saying field for physics. Is that what he's referring to? Like gravitational fields?
Yeah, I mean, look, this is what think about the way Einstein answered this question. So Riemann is saying at the end here, look, in this paper and what I'm doing and giving this lecture, this was a lecture he gave to get a teaching position, and it was in the math department. That's why he says this, we're not going into physics, that's a different department. That's kind of part of where he's saying that literally, right? He says this kind of effort, we're not going to be able to come to specific conclusions, but at least we can make sure that we identify axioms we were unaware of and get really the most general standpoint of looking at things. Let's not make assumptions about space. Let's be open to figure out what is causing the shape of actions in space. And yeah, I was going to say, well, this is what Einstein did, right? Einstein figured out the shape of space from a gravitational standpoint. That doesn't mean that he knows everything or there isn't more to learn, but Einstein gave a shape to space, and it was based on something physical in the realm of physics, a colligating force operating upon it. That is how we define the shape of space. We didn't do it just by measuring how space was curved, although with gravity waves we have done that, but it came from a hypothesis of what is causing space to have a certain shape. I mean, so this is definitely setting up for Einstein here.
So just comparing the keys on the keyboard to the continuous manifold of the string on the cello, you would describe the non-discrete notes that you would be playing according to where you're pressing on the string. yeah, how you're dividing up that string at that time. Right? That's how you would describe or pinpoint the note.
It may be. I mean, what's giving rise to that frequency is where you put your finger.
Yeah, just to simplify it, because there's only a certain amount of causes on the string.
Yeah.
Right? So the light, for example, which is
It's tough because, like, you know, it's clearer, or maybe it's easier to see with multiple dimensions, but I mean, it's hard to come up with any example of that besides space. So color is a little hard to work with. Okay, so we've got some hands up here: Richard Freeman, Joe Jennings, and then if anyone else, now's your chance to put your hand up. Otherwise, that's going to be it, and then I'm going to give a wrap up and point us towards next week and Wednesday. Richard.
Yeah, just on this, what happens is, as you said with Einstein, I mean, it has matter motion, which was raised earlier. There's a matter motion, there's processes. Someone mentioned different fields. There's weak forces, there's gravity. These, some of which you don't see, but it is not completely positionless because it depends where you're moving, as we saw with the question of light, where a particular star was moved when in 1919, when there was a solar eclipse, and where we saw it, thanks to Eddington, was not where the actual star is. So it's this movement, matter motion, through these forces which we don't see, which are very important. But the thing I just wanted to mention from all of this is that these colligating forces create discontinuities, which then tip us off that there must be some principles that we don't know. There's physical discontinuities, they show up as mathematical discontinuities, and that is a spur to then in physics, or in real experiment, which is not empiricism, it's in real experiment, when you say, oh, we've got a discontinuity rather than that's terrible, it upsets my theory, that's fantastic, let's explore that and see if we can go to a higher manifold, which is a series, it's a manifold of principles. So I just wanted to throw that in.
Yeah, let me add to that on that topic. So just coming back to the LaRouche excerpts that we had read at the beginning, we ended with Riemann and geometry in the shape of space, but let's also keep in mind why LaRouche brought this up. In the first excerpt, he says the universe is multiply connected in the Riemannian sense. This has the implication that the addition of a new principle to the manifold results in a change in the characteristic curvature of the manifold as a whole, and indeed the dimensions of the manifold as a whole. And he gave the example of how this would change the impact even of local processes that aren't changed. We brought up the introduction of electric motors. So you can think about this, you know, adding dimensions, 1 to 2, or on a surface 3, we're in space. Think about economy that way. If you're adding a new dimension with electricity, you're adding a new dimension with nuclear science. That's a fundamental change in economics. And the basis of the understanding, like LaRouche says, Riemann's 1854 habilitation dissertation expresses that Platonic principle as its pivotal foundation. What's the shape of space? Big part, that's what are we doing in it? Benoit Odile writes, the measuring instrument is inside the space, so it is curved too. How could it measure curvature then? That's how I understand let's search outside. A really good question. So let's say that we are on a sphere. And you might say, well, if we're our ruler on the sphere, if we're standing outside the sphere, yeah, it looks bent. But you know, it's bent the same way the sphere is so that you can move it around. So what you could do in this case, Benoit, is even though your ruler is curved like the space, if you drew a triangle and you measured the angles, the 3 angles, they're going to be more than 100. They're going to be more than 2 right angles, more than 180 degrees. So the issue of the measuring instrument changing in the space, it is real, but it's not insurmountable. That's one example of how you can figure out what the intrinsic curvature is. That's just geometrical, though. Okay, Benoit's laughing.
Okay, Joe Jennings, you have 1 minute and a half. Richard Burden, 1 minute and a half.
Well, I mean, I also wanted to go back to the very beginning because Lynn in these comments starts with William of Ockham, right, which you really didn't talk any about, and maybe not everyone here is familiar with him. And then he extended that to Euler and Lagrange, and he said that their outlook is satanic, right? That's what he actually said, satanic. And I'm thinking about when Lynn began to generate his hypotheses of the universe, looking at this fellow Norbert Wiener, in the 50s, right? Trying to put limits on things when everything that had preceded him in terms of what happened with our economy in the 1930s, the great transformations, seemed to point in a very positive and expanding direction. So I was wondering if you could just quickly say, why Lynn concluded that these guys were satanic in the, in the implications of where their thinking would take civilization.
Okay, will do. Richard Burden, minute and a half, then wrap up. Richard Burden's hand is down. Okay, so empiricism, it really comes from denying the specific role of the human mind in making discoveries. The idea is that from observations, we can make inductions, we can understand the world in terms of appearances, in terms of measured effects, and it takes us away from the mind coming up with why something is happening. This is how Lynn describes Satanism in this paper, Visualizing the Complex Domain from 2003. He says it's Satanism. He doesn't mean, people, I don't know, with an altar to Bahamut or something. What he means is a denial of humanity. And that's what you do when you say that science is all about data and making inductions from it, and you don't include hypothesizing, where when you make your new hypothesis, you can use it to do something. And that kind of crucial experiment shows, aha, I did something new. Some things get measured by statistics. Okay, this seems to have a 5% impact on that or whatever. But if you make a motor, you have demonstrated something about electromagnetism, that it's not, you have to make multiple data points. It's there. You did something new. It's very clear. And that's what I'd say about that. Look, on Wednesday, we can get more into Gauss, also Riemann, but we can take a chance to get more into Gauss and the complex domain Wednesday if you can make it. If you can't make it, send in thoughts by email. Definitely will respond to those also. And for next Sunday, which is the last class, we're going to be taking a look at how this applies to artificial intelligence, logic, the difference between logic and creativity, and the evil that was perpetrated at a conference of mathematicians in 1900 and its meaning for our lives today. So thank you for joining, and see you Wednesday, Sunday. See you soon.